record. A greenstone of radius r 0.610 meter is being used to sharpen an axe. If the linear speed of the stone is 1.50 meter per second and the stone's kinetic energy is 13 joule, what is the moment of inertia I? So here, what we do have, we are looking for the moment of inertia. So the moment of inertia, we know that is related to the kinetic energy by this formula. The kinetic energy is 1/2 I omega squared. Where we know K, we need to know I, and the only thing that prevents us from knowing I is that we need to know also omega. So our omega is defined as the linear velocity divided by the radius. So the linear velocity here, linear speed, is provided, is 1.50 meter per second. Is also provided the radius, which is 0.610 meters. The units are compatible because here is meter and here is meter per second. So what I'm going to do is only 1.50 meter per second divided by 0.610 meters. And I found my angular velocity, which is 2.46 radian per second. At this point, I have everything I need to know to find I. So I, my moment of inertia is equal to 2K divided by omega squared. So 2 times 13 joules divided by 2.46 radian per second, everything to the square. I performed the calculation and I found that I is 4.30 kilograms per meter square. Okay. And it's normal that is kilogram per meter square because if you remember from the beginning, my I in the most simple cases was a mass multiplied by a distance to the square. So I'm expecting I to be a mass, so kilograms, and then I have the units of a distance to the square. Okay, now, if this is clear, let's move on to something a bit more complicated. Are there questions in the chat that we want to highlight?
I think nothing that I didn't respond to already.
Okay, good. So now let's see another case. In this case, we have rotation plus translation. So you know that when you have, for example, a bicycle, so while in this case is only rotation, so here this object is fixed and move around the axis. In the case of the bicycle, what we do have is that the wheel of the bicycle is not only rotating, but is also moving forward, right? So you have a rotation plus translation. You would have only rotation if the bicycle would be still in one position. Like if you raise up your bicycle and just move the wheels, this is only rotation. But at the moment when you put the bicycle down, because of the friction with the soil, the rotation will also cause a translation of the bicycle. So what you have a motion that is a rotation. So we have omega r here, but it's also a translation. So the wheel is moving, and to move it, remember we discussed about the center of mass. We can consider like the whole wheel like is a dot, if you want, with the one velocity, which is the velocity of the center of mass. So here, no matter where you are considering your dot, could be here, could be at the center, could be at the bottom. Nevertheless, this wheel moves all at the same velocity, linear velocity for the translation, with the velocity of the center of mass. While for the rotation is different. We have zero velocity at the center, when we rotate, we have omega r up here and minus omega r down here. So if I want to put the translation together with the rotation, what is coming out is rolling, what we decide as rolling. So every time in your problem, you're going to see rolling, this keyword. The keyword rolling is translation plus rotation. So in this case, you have to consider that in addition to the velocity of the center of mass, you also have this omega r. So at the bottom, putting these two together, you will have that the velocity of the center of mass is equal to omega r. So essentially at the center, because the center was zero velocity, you're only going to have the velocity of the center of mass. So you're going to have only omega r. At the upper point, you are going to have a velocity, which is the velocity of the center of mass plus the rotation. Velocity of center of mass is omega r. Rotation is omega r. So you're going to have 2 omega r. Velocity at the bottom instead is going to be the velocity of the rotation, which is minus omega r, plus the velocity of the center of mass, which is omega r. So at the end, you're going to have 0. Now, if you look at this, it looks like it will be just the rotation about the points that is, you can consider as it will be a rotation along a point, an axis, which is at the point where the wheel is touching the floor. So it's like it will be rotating around this point, essentially. So we can write all the equations of a rolling object. So the velocity, the linear velocity is going to be r omega. The velocity of the center of mass is going to be capital R, because capital R is really the radius of your wheel, omega. The acceleration of the center of mass is r alpha, where alpha is the angular acceleration. S, if it's asking, is the problem is asking for S, which is an arc of the circumference, is r multiplied by theta, the angle that has been moved during the period of time. And if we ask for the kinetic energy in this case, because remember, it's rolling, and rolling means all the time translation plus rotation, what I'm going to have is that the kinetic energy is the sum of the translation kinetic energy plus the rotation kinetic energy. So translation, we know that is 1/2 mv of the center of mass to the square, and the rotation is 1/2 the moment of inertia omega square. Okay, so this is going to be your kinetic energy. I hope it's clear for you. So this is the translation, the one that you have been using so far when you have a linear motion. This is the one that you've learned today that you have to use when you have something that is just rotating. The kinetic energy of a rolling object is the sum of these two, because both of those motions are taking place. So when I speak about the total mechanic energy, what do I have? I have the kinetic energy, which is the kinetic energy of the center of mass, plus the kinetic energy of the rotational movement, plus our potential energy. So the mechanical energy is 1/2 v of the center of mass to the square, which we know that is also omega r, right? Plus 1/2 I omega to the square, plus mg y of the center of mass. So instead of treating the rotation and translation separately, we combine them by considering that instantaneously the system is like rotating about the point of contact. So the point of contact is instantaneously at rest. like it was the axe, like it was in the pure rotation, the center of the axe. And so here, yes, this we already discussed. So in this case, well, let's don't look at these things. Let's move on. So for the conservation of energy, the total kinetic energy of a rolling object is the sum of the linear and rotational kinetic energy. So let's see an example. We have a rolling disc. So rolling disc, again, I see the word rolling and I immediately understand that it's translation and rotation. And then it say a 1.2 kilogram disc with the radius is a disc. So when I go for the momentum of inertia, I need to look for the one of a disc with a radius of 10 centimeters that rolls without slipping. The linear speed of the disc is this. Find the translational kinetic energy. Translational kinetic energy, I know that is kT 1/2 mv squared. So 1/2, I have the mass of the disc. Yes, is in kilogram, which is fine for me. Good. Velocity, I have the velocity 1.41 meter per second. Units are good. I can just use it as it is, to the square. So it comes out to 1.19 joules, which is the unit for the energy. Then find the rotational kinetic energy. In this case, I have 1/2 I omega square. 1/2 I need to look the I of the disk. So we go back. 1/2 mr square, right? A disk that is rotating around its axis. Let me go back. Okay. So here is 1/2 mr to the square, omega square. Omega is b divided by r to the square. I know all these quantities, so I just substitute the quantities. They are also in the correct units, and I found 0.595 joules. Very good. Find the total kinetic energy. The total kinetic energy is the translational kinetic energy plus the rotational kinetic energy. So I just have to put the sum, this term with this term, and it's coming out to 1.79 joules. Okay, are there questions on these things?
Yeah, there was a little bit of a question a couple slides back when you first showed the bicycle wheel rolling. Could you show slide 8 briefly?
Yes.
Great. Okay. So one question was, what does the little subscript I represent in this slide? I think it's referring to one tiny little piece of mass of the wheel. Would that be correct?
Yes.
Okay. So if we think of just any one little tiny piece of mass of the wheel, then the ith piece of mass of the wheel has a velocity that's equal to the center of mass velocity of the entire wheel, plus, well, I guess it'd be that, plus the relative velocity of that ith piece relative to the center. So that would be like on this case right here. Okay, so if we add those two velocities together, then we get what an observer standing off to the side would see as the total velocity of that ith little piece of mass.
Yes.
So
this is a more general equation to write all the possible velocities. But
so folks, and I would say that students who are watching, you don't need to worry too much about that derivation.
Yes.
Veronica, could I emphasize one more thing about
the
formulas we're using for rolling objects? Okay, this relationship right here, that the center of mass has a velocity equal to omega times the radius of the object that's rolling. It's only true if the object rolls without slipping. Okay, So in other words, and rolls without slipping. So in other words, like Dr. Bindi was saying, this point of contact here has to grip the surface below. Now, this is true for most objects we see all the time, right? So cars and bicycles normally do this unless they are skidding, right? If they skid, then all of a sudden this relationship is not true. If any of you bowl, if any of you do bowling, then when you first release the bowling ball, it slides along the ground and this relationship is false. And then only after the ball gets rolling so fast that it grips the ground, which is usually partway down the bowling alley, then all of a sudden this relationship holds, okay? All right, so same thing is true if you play pool or billiards. You can make the ball slip or spin in various ways, but it's only after the ball is rolling normally and gripping the surface that this relationship is true. Fortunately, that's the only type of problem we're going to deal with in this class. we're not going to deal with any of the slipping or skidding type problems. That we save that for the physics 170 students. And I have one last observation too, if I could, on slide number 8. This view right here, this is what the bicycle rider sees. So when next time you're riding a bicycle or a motorcycle, take a look down at your front wheel. And what do you see? You see the center sitting at rest, you see the top edge going forward, and you see the bottom edge appearing to go backward along with the ground, right? That's what you appear to see. Whereas an observer on the ground standing nearby would see the picture on the right. An observer on the ground sees the point where your wheel touches the ground as remaining at rest. The observer sees the hub or axle of your wheel going at the same speed as the rest of the bicycle and you forward. And the observer momentarily sees the top edge of your wheel going very fast, right? Twice the speed of the whole bicycle as a whole. So I don't know if that helps students to sort of understand these two views a little better, but even if you don't, you can just use the formulas like are in these examples that we're doing. So, okay, great.
Yeah. And also, so they were asking here, you see is positive. So imagine that you have a pin here. Imagine that you put a pin on your wheel while you are going. So here the velocity while you are going further, if you look from the top, the velocity here is going straight in front of you. But the pin, when it gets here, it moves, moves, moves. The pin, when it gets here, the velocity tends to go in this direction, if you think about it. It doesn't go like this. If it will go like this, is this case. If it will be both of them positive and in the same direction, it will be a translation. It wouldn't be a rotation. For a rotation, imagine you can even put your hand and move your hand in a way like following the rotation, and you will see that if your fingers are indicating one direction at the top, at the bottom they are indicating in the opposite direction. So it gets normal to have this. I don't know if Yuna, if this helps you to understand. Okay.
Great.
Then,
Thank you. Thanks.
where were we? Oh, okay. We saw this example, and you see, so it might be scary, but then in the reality, the problems are pretty much straightforward and are all very similar to what we are showing right now. And so then let's see another problem. This is conservation of energy. A bowling ball that has a 11 centimeter radius and 7.2 kilogram mass is rolling without slipping. So again, the keywords rolling without slipping. So rolling, translational plus rotational. At 2 meters per second on an horizontal ball return. It continues to roll without slipping up at the hill to get a H before momentarily coming to rest and then rolling back down the hill. Model the bowling ball as a uniform sphere and calculate H. Okay, so here we get to this problem, which might be even more complex than the one that we we give you to the homework. This, I don't know, Mike has to comment on this, but so this, we have a conservation of mechanical energy. So what we write is that the final potential energy plus the final kinetic energy has to be equal to the initial potential energy plus the initial kinetic energy, right? This is the conservation of energy. Then final position, what do we have in the final position? So it says that is continued roll without slipping up the hill up to a 8H before momentarily coming to rest. So when it gets at H, of course, the ball is at rest. So here I have in the final position, I have the maximum of the potential energy, which is mgh, remember, gravitational potential energy, plus my kinetic energy at this point is 0 because the ball is at rest. And this is the final position. In the initial position, instead, what I have a potential energy, which is 0, because I consider like the bottom here is the 0 potential energy, plus, because essentially H is equal to 0 at that point, plus what? Here, normally you would have written 1/2 mv squared, which is the kinetic energy. But because this is a ball and rolling without slipping, you have to consider also its angular, its rotational kinetic energy. So 1/2 mv center of mass to the square plus 1/2 I omega to the square. Okay, now you need to find the I of center of mass of a sphere. Okay. And we have it that is, I can go back to the slides, but you are going to see that it's 2/5 mr squared. So here we have mgh is equal to 1/2 m v center of mass to the square plus 1/2 2/5 m to the r square v center of mass divided by r to the square, because omega I, we know that is, this is the formula, is v over r. Okay, so if I do all the calculations, I found out that is here, summing up the things together, it comes to 710 mv to the square. So I can find at this point h, which is 7 v of center of mass divided by 10 grams. Okay, because here h, so I essentially divide by m, so m goes away. And so I found that h is 710 v center of mass divided by 10 g. Okay, yes, so you simply remove the mass. So at the end of the day, is independent from the mass of the object. And h is 7 v center of mass to the square divided by 10 g. And you know all these numbers, so you just find 0.29 meter. Are there any questions about this problem? Mike, do you want to?
Not in the chat. Well, the chat is currently one student asking about how hard are different homework problems and what do we need to know for the exam and things like that. So not about this. Do any other students have questions about the rolling example here with the bowling ball? Maybe unmute and speak up.
Because if not, we can move to the next topic.
All right. And Veronica, you asked about whether this is relevant for 151. Yes, this is. So there's at least one, there's a couple of mastering physics problems on rolling objects just like this. And as well as in pre-recorded lecture 25 at the end, and one of the tutorial sample problems. So yes. So
no, this is really, it's normally a very important topic. And you see most of the things you already know, like the conservation of energy you already know, is only the fact that now you have to consider the kinetic rotational energy and the momentum of inertia. The momentum of inertia, you see, you get it from these tables. And then the kinetic energy, the rotational kinetic energy, you know the formulas, right? So you have these two, because it's all the time translation plus rotation. So I think you can do it. Yeah. Then let's move to a new concept, which is torque. So from the experience, we know that if we apply the same force, it will be much more effective at rotating an object, for example, depending on the position where you push it. Like if you look at the case B, right? You see, if you apply the same force, assume you apply the same force, it will be much more effective if you applied here at a greater distance from the rotation axis rather than a smaller distance, okay? So in this case, we consider the torque the ability of a force to cause a rotation or twisting motion, which depends on the force of the force, the magnitude of the force, the distance at this point from the point of application to the pivot, and also the angle at which the force is applied. So again, imagine that this is the top view of the door and this is the hinge. If you apply a force here with respect to a force here, F1 will be more effective than F4. But even if you apply here F1 will be more effective than F3, right? This comes from your experience. And imagine if you apply the same force here. If you apply the same force here, you get nothing. Essentially, the door doesn't open, right? So this comes from your experience. So the torque is essentially, we define a new quantity, torque indicated like this, which is R force sinus of theta, where theta is the angle between the radius and the force. So this is the force, this is the radius, and this is the angle. This is the angle, sorry, between the radius and the force, okay? So, for example, if we need to visualize it, if this is the force, tau is R F sin theta. F sin theta is essentially the component of the force along here, perpendicular to R, okay? So we already saw that the most significant force is the one that is to make rotating this object is the one perpendicular to the radius. Now the units are Newton per meter because we are speaking about the force multiplied by the distance. So Newton per meter. And the torque can be considered as the distance r from the pivot to the point of action of the force times the tangential force component. So we are only considering the tangential force, which is the most effective to apply the rotation. How is the sign of the force, the torque? So if the torque has a counterclockwise angular acceleration, it is positive. While if it causes a clockwise angular acceleration, is negative. Okay, so here counterclockwise is positive, while is clockwise is negative. And this you can also see using sinus of the angle. You're going to be able to see. So essentially, when we speak about angular quantity, instead of the mass, we want to speak about the moment of inertia. Instead of the acceleration, we are speaking about the angular acceleration. And instead of the force, we are speaking about the torque. So as we have that the force is ma in angular quantities, we have that the torque is IA, alpha, I alpha, where alpha is the angular acceleration. Okay, so you see, because as I said before, when you're speaking, so when we are speaking about linear motion, essentially the force, as we saw, is mass time acceleration, and it's easier to understand. But when you speak about the angular, the rotational motion, then, as we said, some components of the force might not be important. So the only one that is important is the one that is perpendicular to the radius, as we saw here, okay? Not this one, it's only this one. And so that's why we see how the torque is somehow related to the force. And so we can write it again as momentum of inertia multiplied by the angular acceleration. Now let's see an example. To get some exercise without going anywhere, you set your bike on a stand with the rear wheel free to turn. As you pedal, the chain applies a force of 18 Newton to the rear sprocket wheel at the distance of 7 centimeters from the rotation axis of the wheel. Consider the wheel to be a hoop of radius 35 centimeters and a mass m 2.5 kilograms. What is the angular velocity of the wheel after 5 seconds? So here what we have is that the net, because it's so you have rotational motion. Here we have our torque. Torque is equal to Frs. We know that is the force multiplied by the radius, but is also equal to I multiplied by alpha. So the force here is perpendicular. So the sinus of the angle is 1. So is only Frs equal to IA, I alpha. So I can find from this relation, I can find alpha. Alpha is equal to the torque divided by I, which is equal, torque is Fr divided by I is mr to the square, because it tells you here to consider the wheel to be a loop, a hoop. If we go back to our, this is a hoop, I is mr square. Very good. So we go now back to our problem, mr square. Okay. Now we have that omega is equal to omega naught, which is the initial velocity, plus alpha t. Initial velocity is equal to 0. Alpha t, we just find alpha, and we have to multiply by t, which is 5 seconds. So force 18 Newton. Now, all the dimensions are in centimeters, so I need to bring them to meters. So 7 centimeters is 0.07 meter, divided by the mass, which is 2.4 kilograms, divided by the radius, which is 0.35 meter to the square, multiplied by 5 seconds, and essentially I find that omega is 21.4 radian per second. Are there questions on this problem?
Nothing about torque so far.
Okay. Then when we discuss about static equilibrium occurs when an object is at rest, neither rotating nor translating. Or for an extended object to be in static equilibrium, it needs to have the following conditions. So the sum of the forces in all the components, X, Y, Z, linear component, the net force acting on an object must be zero. So this force needs to be zero, but also the net torque acting on an object must be zero. Okay, so the sum of tau needs to be zero. Very good. So if there are no more questions, we can go to the last topic, which is very important, and unfortunately we arrived a bit too late, which is the definition of the angular momentum. Angular momentum L is I, moment of inertia, multiplied by omega. So you saw the momentum P, which was M times D. And here, instead of mv, we have capital L, because this is the angular momentum, I replacing the mass, and omega, which is replacing the linear velocity. Now, because I is mr to the square, and because omega is v divided by r, L is also equal to rmv, which is also equal to r multiplied by the momentum. Okay, so essentially you have R, the mass, and the velocity. All these information are together in one quantity, which is called angular momentum. Now, angular momentum goes in the same direction of the angular velocity. So angular velocity and angular momentum vectors point along the rotation axis in the direction determined by the right-hand rule. The right-hand rule, how does it work? So you essentially move all your hand, like you see in this picture here, you put all your fingers moving like the arrow below, and the thumb is indicated the direction of omega. So we can treat rotation and other angular motion quantities as vector by using this right-hand rule. If the fingers of your right hand follow the rotational direction, then your thumb points along the rotational axis in the vector direction of the angular velocity omega. Okay, you see also here, omega is going in this direction. If omega is going this direction, also L is going in this direction, because L is omega multiplied by I, and I is a scalar quantity. So the vector direction of the angular velocity omega and the angular momentum vector L are along the axis of rotation. And you have to apply the right-hand rules. I don't know if we have some time, but yeah, let's see. The spin angular momentum of the Earth. What is the angular momentum of our planet as is rotated along this axis? Omega is 1 revolution every 24 hours, but to bring it to seconds, we have in 1 hour, we have 3,600 seconds, and then 2 pi radians means 1 revolutions. And like this, we got omega as a 2.27 10 to the minus 5 radians per second. So we move from 1 revolution per hour to radians per second. Then we have I is 2/5 mass of our planet, radius of our planet to the square. So we multiply and we find the moment of inertia of our planet. L is I omega, and we just find I, and we have omega. And so this is L, the angular momentum of our planet. Conservation of the angular momentum. If the net external torque of a system is 0, remember, so the sum of all the torque, all the angular forces acting in our object are 0, the angular momentum is conserved. The most interesting consequences occur in systems that are able to change shape. You see with this drawing here, but you can imagine also with the ballerina where she's spinning around with the open arms, and then you see when she closes her arms. So look what happens. So Li initial is equal to, so the initial angular momentum is equal to final angular momentum, which means I omega initial is equal to I omega final. Omega final, so is equal to I initial divided by I final omega initial. So in this case, if we have 3.74 radian per second, and you see the guy has open arms on top of a chair that can twist around. If he closes, as soon as he closes his arm, our angular moment, our moment of inertia changes from 5.33 kilogram per meter square to 1.60 kilogram per meter square. And so we see our angular velocity changes from 3.74 radians per second to 12.5 radian per second. So is speed up, okay? Is speed up. And here there are other examples, but maybe the last example, but the time is over. So I don't know, you can do it from home or we can do it next time.
Actually, that the guy right there spinning on the stool, right? That's what I call the classic ice skater example. That's perfect.
Yes.
Yeah, we're not going to do like coupled systems in you know, beyond like yeah, we're not going to do like coupled spinning systems.
Yeah.
Great. Well, thank you, everyone. So Julia will have office hours here on Zoom for another hour now. So if you're welcome to come back either to see her, or Ewan is also going to be on Zoom and in Watanabe 415 starting at 11:30. So you can either see him in person or on Zoom.